Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant as a review of concepts from your prerequisite algebra class. As such, I don't delve into the proofs of theorems here, nor do I go into excruciating detail with examples. If you get lost with the concepts in this video, and it's been a while since you took algebra, I highly recommend watching my full lecture videos on this topic, which can be found in my Algebra Lots About Linears playlist on YouTube. But if you're okay with it, let's continue forward. We're going to start talking about systems of linear equations in 3 variables. Now, this lecture is really for college algebra students, so there's no review of systems with 2 variables. You've had several courses on that already that covered that topic in excruciating detail. In this case, you still have actually seen systems of equations with 3 variables, but it's good to kind of review a few topics within here. So we're going to start with a review of the types of systems of equations that you can run into. That's what this video is dedicated to. So let's start with a quick recall, a definition of a system of equations. It's just a set or a collection of equations that must simultaneously be satisfied, and that is called a system of equations. So let's go ahead and just write down a few examples. And that right there would be called a 2x2 system of equations, 2 unknowns with 2 equations. And normally we use a brace to kind of group those things together so you know that those must be simultaneously true. That's what we're looking for that. And that would also be called a system of linear equations specifically. And that is because both of the equations in this system are linear equations. Another way to think about that is that they involve variables, x, y, z, whatever, and the powers on those variables are all 1. So they are linear equations. This second system is also a system of linear equations. The variables are weird looking. It's because they're in Greek. It's just alpha, beta, and lambda, but it's still just like an x, y, and a z. And the powers on all of those variables are 1. So this is a system of linear equations, and it's a 3x3 system of linear equations. It is written in such a way, in fact, the previous system was as well. It's written in such a way that most people would like to kind of readjust these and get all the variables on variable terms on one side and all the constant terms on the other side. So this is not what I would call a standard form for a system of equations. Most of us would love it if alpha, beta, and lambda terms were on the left-hand side of each of those equations and the constant terms were on the right-hand side. They don't have to be, but that's really what we would prefer. And up here in the upper right hand quadrant, we have another system, and this is a non-linear system. It's non-linear for a few reasons. First, there are variables with powers other than 1. So that immediately makes the system non-linear. But if all those powers were, let's just pretend 1, it's still non-linear because you have a function of x, and that function is not just the first power of x, it's the cosine of x. And so it's a non-linear system of equations no matter what. And this really would be very difficult to solve, to be honest with you, but it's still asking the same question. When are these 2 equations simultaneously true for what ordered pair x, y, or is there an ordered pair of x and y such that it solves the first equation and the second equation simultaneously? And that actually might not exist. Now with this slight adjustment right here, there is a solution to this one. I know there is. X equals 0, y equals 1. But that would be incredibly difficult to find that solution by hand. So this is just a heads up that systems need not involve just x and x to the first and x, or x to the first, x to the second, x to the third. They can involve a mixture of transcendental functions and algebraic functions. And just as an example, here's yet another nonlinear system of equations. Now, these two on the right-hand side, the nonlinear equations, is not the purview of the discussion for this video series currently. We will get into systems of nonlinear equations eventually, but they will definitely not be of this caliber. Normally, something like this, you would use some type of computer algebra system or some type of software. Now, systems of equations can be split into two disjoint groups. Those are the consistent systems and the inconsistent systems. Now, a system of equations with at least one solution is called consistent. And rather than creating equations, let's just look at some visualizations of what these might be when you're talking about a 3x3 system. Now, the following is a Wolfram Demonstrations project applet here, and these are free. You can just Google Wolfram Demonstrations and it'll bring this up, not this specific one, and then you can search for systems of equations and see the visualization. The equations that are in question here are 3x plus 2y plus 3z is equal to 3, and then you can see the equation in purple, and you might be able to see that equation in gold. Let me see if I can zoom in a little bit here. There we go. So in this case, we have three equations, and each equation involves three unknowns. Well, that type of equation is no longer a line when you have powers of 1 on all your variables. It's still called linear, still called a linear equation, but it's not a line. It's actually a plane in 3D. And you could see there are three pieces of paper. Those are planes. There's three planes on this graph here. Each of those planes, let's see, the green plane represents the solution set for the green equation down here. The purple plane represents the solution set for the purple equation, again, right here. And the gold plane represents the solution set for the gold equation, which again is at the bottom right there. And where they meet simultaneously is called the solution. So where all three pieces of paper or planes intersect would be the solution of the system. And you can see that little red dot there. That's the actual solution of the system. So because it has at least one solution, this system would be called consistent. Now we can adjust the equation slightly. You can see that the green equation now is just negative 5z is equal to 0. And you can also see the other equations there. But these are just sheets of paper that are now perpendicular to each other, or what we would call orthogonal to each other. And they still meet at a single point, that single red dot. So this is still a consistent system. A little more subtle is this type of system where you have two perpendicular planes and then a plane that intersects them, but is also, it intersects them along a line. So everywhere all three of those planes touch is the solution. And since there's at least one solution, this system still would be considered consistent because, again, it has at least one solution. Wherever those three planes intersect simultaneously, that would be called a solution. You could see that it's very kind of hard to see, honestly, but there's a red line there. It showcases all the places where these planes meet simultaneously. So this is still considered a consistent system. And the very rare system in 3 dimensions is the one where all three equations are the same. So all three pieces of paper, or all three planes, lie on top of one another. There's an infinite number of solutions here because, well, they touch everywhere. All three planes touch everywhere. So therefore, this is still consistent because there's an infinite number of solutions. In other words, there's at least one solution. So it seems like there's a lot of ways to get a consistent system, at least when you're dealing with a system of 3 equations with 3 unknowns. However, there are 3x3 systems that are called inconsistent, and inconsistent systems are systems of equations with no solutions. In other words, you have a bunch of equations, that form a set of equations that you want to find a simultaneous solution to, and yet there is no simultaneous solution. There's not a solution that satisfies all equations simultaneously. So let's take a look at what this may look like in 3 dimensions. You can see it right here. You have 3 planes, and you're looking for where they all intersect simultaneously. And if you look, while 2 planes do intersect, for example, the green and purple intersect along a line right here, and the gold and purple intersect along a line right there. And if you look in the other direction, the green and gold intersect along a line. So any 2 planes actually do have an infinite number of solutions, or an infinite number of intersection points. All 3 planes never simultaneously connect. There's just not a single point in space where all 3 planes intersect. So this is an inconsistent system because there's no solution. There's no place where they all 3 connect simultaneously. Now, it turns out that consistent systems, those that have solutions, are further broken into 2 subgroups, those which are called dependent and those which are called independent systems. And to be very honest with you, that definition of dependent and independent systems really truthfully should be dependent equations and independent equations. However, it's very hard to find a good, clean definition that involves dependent equations and independent equations. So we'll just use this. So a consistent system with an infinite number of solutions is called a dependent system. Again, it really should be called a consistent system with dependent equations, but that's okay. We just call it a dependent system because most people do, even though it's actually not correct. And if it only has a finite number of solutions, so you have a consistent system, so it has solutions, but the number of solutions is finite, maybe 1, maybe 2, maybe 5, okay, we would call that an independent system. So it's consistent with independent equations is really truthfully what it should be called. So if we go back to that applet on Wolfram demonstrations, we could see which ones are considered dependent and which ones are considered independent. For an example, this picture right here, you could easily see there's only one solution, a finite number of solutions. Therefore, this is not only consistent, but we'd call this a consistent independent system, or a consistent system with independent equations. The same thing for this one, the second one that we had in line, where again, your planes in 3 dimensions meet only at a finite number of points, specifically at this one point. So therefore, again, it's a consistent system of independent equations. On the other hand, this guy right here, these 3 planes meet at an infinite number of points. Every point along this line they meet. There's an infinite number of spots where these 3 planes meet. So while this system of equations is totally consistent, it absolutely is, it is a consistent system of dependent equations. So we would call this system dependent. It's a consistent dependent system. And finally, we have this consistent system, which is 3 planes lying on top of one another. And because they're lying on top of one another, they touch at an infinite number of points. So again, it's a consistent system of dependent equations. All the equations are the same in this case. So if you're working with a 3x3 system, a 4x4 system, nonlinear equations or linear equations, all the definitions are the same.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.